X-rays. We have worked with this type of ionizing radiation a few times in the nuclear lab, but today we are going to take a look at it from a medical point of view with a small focus on radiation protection. So anyone who needs a rough overview because they work in this field, hopefully this video is for you. Before we get to the fun part, the hospital procedure, let's start with the basics. Where do the X-rays come from? First of all, X-rays are high energetic electromagnetic radiation. It is so high in energy that it is classified as ionizing radiation. Ionizing, for all practical purposes, means that it can cause damage, so be careful. In an X-ray tube, as here in the hospital, electrons are accelerated in a vacuum with a voltage up to 81 kilovolts. The negatively charged electrons, they are always negatively charged, hit the material of the positive pole. On impact, they are slowed down. And there's a rule in physics that says when electrically charged particles change speed, in this case when they are slowed down, they emit electromagnetic radiation. This is the majority of the X-rays we are working with. Since this is generated by de-acceleration of electrons, it is called braking radiation, or in German Bremsstrahlung. The electrons do not come from anywhere, but they come from a glow cathode that must be made from a heat-resistant material. Tungsten, for example. As a result, electrons flow and the current flow is described with a voltage of approximately 20 volts and 3 to 8 amperes. The high voltage can then be used to release and accelerate these electrons from the glowing cathode, so it's a really high current. And the release of the electrons is made easy because of the high current and the high heat. They indirectly vibrate. There are different sizes of glowing cathodes within the same X-ray tube in a hospital. The selection is here made, for example, via the buttons and depends on what you want to image. Small is good for smaller objects. Always adjust to protect the tube primarily. If you give this device the input shoulder, for example, it automatically switches to a larger cathode. A vacuum inside the X-ray tube is required, otherwise the electrons cannot be accelerated evenly. The higher the acceleration voltage, the more energy the electrons bring into the anode material. This means that the braking radiation has more energy. This is initially bad for use on patients. The more energy the braking radiation brings, the higher the radiation exposure, and this is what must be minimized. In a simple X-ray tube, the electrons would simply fly out to the cathode in a shape of a cylinder and generate a lot of X-rays that are useless for imaging. A so-called Venelt cylinder is used to focus the electron beam. The electron beam is focused with a separate voltage. That's all well and good, but let's be realistic. The primary electrons do not hit the anode perfectly at one point, and the braking radiation will also not be generated at one point either. This is not so bad in most cases. At first glance, a related effect is the Heel-Effekt. This is often wrongly attributed to this uneven impact, but this is not the case. The Heel-Effekt describes the self-absorption of the braking radiation by the anode material. This reduces the radiation exposure in this exposure area, as the radiation has to pass through more anode material. In addition, we have even more radiation exposure in this area due to extrafocal radiation. In other words, some electrons can bounce off the first impact, are accelerated again, and then generate new braking radiation. Now it is important to know what the anode material is made from. It is often copper or molybdenum. These are two elements in the periodic table, and accordingly they have different atomic structures. In addition to the so-called braking radiation, there is also characteristic X radiation. This is produced when electrons are knocked out of the atoms of the material. These gaps are quickly filled, but this is not done randomly, but by certain shells. And these energetic shell differences are atom specific. Accordingly, copper anodes have different specific X-ray lines than molybdenum anodes do. However, these are values that you can simply look up if you're interested, link in the video description. Now we need some more basics about the atomic structure in order to understand the so-called characteristic X radiation. One of the inner electrons is knocked off the shell. This can be caused by the de-accelerating electrons or by braking radiation, and is then replenished by the upper shells. The shells have defined energy distances. If they are filled from up here, the energy difference is greater and therefore the characteristic X radiation has more energy in this case. It is shorter in wavelength than if it is replenished from this shell. We can use this device now with the basics in mind, but at some point we should add another theory part when it comes to the finer points of the operation. Right now we are imaging. However, we can only measure the natural background radiation as the glass contains lead. This is radiation protection glass. It does not contain so much heavy metal that it's colored like in the nuclear laboratories, but it still provides protection. The strength of the electron beam, which also results in the intensity of the X-rays, is set on such a console. Here are the most important information to describe the intensity. The electrons are accelerated with 50 kilovolts. The total amount of charge that flows is 2.5 milliamps, and keep in mind that not every panel works the same way. For some, the amount of charge and time must be set separately. The maximum for this console is 81 kilovolts, but you use that if the patient is obese. As the voltage is higher, the X-rays are harder and therefore can penetrate more material, in this case human. But a case where you would use this high of a voltage, that would be a lung X-ray without grid and on the stretcher. Typically you don't go any higher with this tube. In addition, a wrist, for example, is sounded here. It arrives anterior and leaves the hand posterior to hit then the X-ray plate. This is what the device looks like. The X-ray tube accelerates the electron in this direction. This can be seen from the minus on the one side of the device. The braking anode is ring-shaped and rotates so that it lasts longer and the accelerated electrons do not keep frying the same part over and over again. This can also be heard by the patient when switching on the X-ray tube. Of course, there are also some lead shields to minimize the amount of radiation passing through. The aim is to keep the radiation dose as low as possible. Speaking of keeping the dose as low as possible, you can adjust something else on the device when it comes to imaging children. Namely, you can turn 1 mm of aluminium and 0.1 mm of copper in front of the tube so that the scattered radiation is reduced. This is called hardening. Scattered radiation is also exactly the reason why an operator must close the door during the imaging procedure. This plate is turned off for adults, otherwise the images becomes Ideally, you will always want the X-ray film to be as close to the object as possible. The object casts a kind of X-ray shadow due to the absorption of X-rays by the bones and other tissues. And the further away the object is from the plate, the more blurred the shadows becomes. This is normally hardly a problem unless the patient is lying in a bed and the object to be X-rayed is the ribs, for example. One more brief insertion about the chest. If you want to expose from the side, this would be an advantage as the heart is close to the plate in the orientation and it does not appear that the patient has an enlarged heart. Stuff that you want to avoid. Exposing the ribs when laying down. The plate has to be placed under the table and the ribs are quite far away and cast an inaccurate shadow. However, there is a solution that is also built into the table for this. A scattered beam grid is built into the table under which the digital X-ray film is first placed. Scatter ray grids ensure that the image comes out sharper because only X-rays arriving in parallel can pass through the grid. But at the same time, this means that we also have to use more X-rays to offset this and generate the same quality image, because some of the X-rays are lost by filtering them out. This again increases the dose for the patient. This is something that can be justified because you will have to take fewer pictures. But again, that is something that you cannot justify with children. So for children, turn in the plate in front of the hand and take it out behind the hand. Is there anything else that can be done to reduce the radiation dose? Of course, giving the patient lead shielding, depending on which parts of the body need to be photographed and which important parts are in direct vicinity. Just normal shielding would be boring, but we have testicular capsules. The penis should not go in there. It normally shouldn't even fit in there. A disposable film goes in there for protection, don't worry. But of course, if the hip is exposed, you need something like this. Of course, it is not placed in front of the measuring chamber, otherwise we'll have to expose twice and that would not be in interest of radiation protection. And for the woman, there are these lead butterflies. You kinda have to be able to feel it and place it accordingly. That Heel-Effekt that we just learned can also be used for radiation protection. So now that we know how the X-ray beam is created, how to set it up, what precaution you should take when exposing, and now how is the X-ray image actually created? These are memory foils. which are regularly checked for defects and are reusable. They are read out in a device that looks something like this. Yes, this is a bit outdated here, but at least no X-ray films are used anymore. We have a protective layer so that the storage disk is not damaged. And now there is a distinction made between PIP and NIP disks. The PIP is also a scintillation crystal in powder form, a powder image plate. The scintillator is a barium fluorohalide. Barium fluoride and two other halides called bromide and iodide form the main part of the crystal, and the scintillating properties are caused by specific europium impurities. This is so-called doping. The same occurs with thallium-doped rubidium bromide. In any case, this powder is held in a binder and is randomly distributed in larger and smaller grains. I'm assuming that this might be outdated, but please teach me better. There are also NIPs, i.e. needle image plates. These consist of finely arranged needles on doped cesium bromide. This doping is now very important because the rare earths, such as europium in most cases, can be excited by X-rays and their electrons can be put into a very high energy state. The electrons remain there for the time being. The incoming X-rays are therefore initially stored in the energetically raised electrons in the crystal grain. The energy can then be partially released again during the readout. To do this, a helium neon laser is shown onto the storage disk via a mirror. If the laser beam now hits the electrons of the exposed crystals, the electrons can release some of their energy. They do this in a form of light, mostly blue light. The technical term for this is photoluminescence. Sometimes it could also be green light. And depending how much the individual crystal glows due to the laser excitation, you can then calculate back how much radiation this individual grain has received. If you do this for each crystal grain, you can put together an X-ray image pixel by pixel. There you have it, the X-ray image is ready. It may well be that not all electrons are released from this excited state during the scanning, in which case you wipe it off all again with a very high intensity light, and then the image plate should be ready for the next X-ray exposure. A big thank you goes out to all my Patreons. Thank you for your financial support. And with that being said, thank you for your attention and goodbye.